Okay. Today we start to study numerical linear algebra. Okay. I have sent you the book in PDF file. Okay. So download the book. But the book is free. No, free to download. Yeah. Right. Okay. Two main topics about numerical linear algebra. One is compute eigenvalues of a matrix, compute eigenvectors. The second main topic is solve linear systems. Right? Okay. All the matrix size is huge. If you go to industry, what in industry, okay, this is a common, okay, billion size, billion by billion, okay, common, okay, not just 10 by 10, 5 by 5, in the exercise sections in the book. No, those are toy problems. Okay. Now today I first present how to compute eigenvalues. Okay, eigenvalues. Take a review about what is an eigenvalue of a matrix. What is an eigenvector? Okay, yeah. Here is the definition. Assume matrix A is a complex matrix size n by n. Okay. If you can find, okay, a scalar in the context of linear algebra, number is called a scalar. Okay, a scalar, complex number, is an eigenvalue of matrix A if you can find some non-zero vector. Okay, if there is a non-zero, okay, non-zero vector. The vector say vector B also complex. Yeah. Cn n is the length of the vector. The vector has n entries. Such that this equation is true. Okay, it's true. Yeah. Then lambda is eigenvalue. V is associated eigenvector. Okay. If there is a non-zero vector V such that this equation is true, okay, then lambda is eigenvalue and V eigenvector. Yeah, this is V. Eigenvector. Yeah. Associated with eigenvalue lambda. Theoretically, we know how to compute all eigenvalues and eigenvectors. Yeah. Theoretical. Yeah. Right. This is a field. Okay. Field. An eigenvalue, say lambda 0, must satisfy, yeah, this equation. Okay, matrix A minus lambda I, yeah, then take determinant 0. Yeah, an eigenvalue must any eigenvalue. Okay, must satisfy this equation. And what is the left side? Left side determinant. If you expand the determinant, you will see left side actually is a polynomial. Yeah. When you expand, okay, yeah, expand is determinant. Expand it, then you will see it is a polynomial. Polynomial, yeah. Polynomial in lambda, okay, in lambda of degree n. Then to find all eigenvalues, just find all the zeros of the polynomials on the left side of this equation. Theoretically, okay, but computationally doesn't work. Why doesn't work? At the beginning of the semester, I show you one example. Okay, determinant just a 20 by 20 determinant, 20 by 20 determinant. Okay, determinant. Expand 20 by 20 determinant and use a supercomputer. How fast the computer? 10 to 10. 14 point operations per second. Okay, second. Yeah, 1 second, then perform 10 to 10. 10 to 10 is 10 billion, right? 10, I don't know, 1 billion, at least 1 billion. Use a supercomputer to compute 20 by 20 determinant by expansion. Take, I don't know, take 100 years to get the result, right? 100, yeah, you need to go back, okay, the example, okay, take a long time. So if you expand the left side to get a polynomial, then compute the zeros of the polynomial, doesn't work. Okay. Then how to find eigenvalues efficiently? Okay. Yeah, this is what we are going to study. We're going to study. Hey, now today, I present the first method. Okay. Power method. This method only compute the largest eigenvalue and the eigenvector associated with the largest eigenvalue. Okay, this method. Okay. Then later on, I will present a method. The method efficiently compute all eigenvalues simultaneously. Okay, now take a look at power method first. The first method. To present the power method, let's make some assumptions. Yeah. Assumptions. Number one, we only consider real matrix. Yeah. Even though the matrix is a real matrix, its eigenvalues can be complex number. Okay, now we make assumption. Okay. Number two, all eigenvalues. Yeah. All eigenvalues. There are n eigenvalues. Are real numbers. Okay. Yeah, make these assumptions. Because I know the power method I present here is the basic one. Okay. How to handle complex eigenvalues? There were many research on the topic. Okay. And we have obtained algorithms that can handle all the situations. But here I only present the most fundamental, the fundamental one. Okay, fundamental one. Yeah. All right. Eigenvalues are real numbers. Matrix A are real. So all eigenvectors are real. Okay. So together. Okay. A1, 2 together imply all eigenvectors are real vectors. Okay. Yeah. 1 and 2 together imply all eigenvectors are real, okay, in Rn. Okay, in Rn. Further, I may continue to make assumptions, okay. Power method compute dominant eigenvalue. Compute the eigenvalues that is the largest in absolute value. Let me make assumption, okay. Yeah, this one is the dominant eigenvalue. What it means? Okay, assume lambda 1 in absolute value greater than lambda I. Okay, for I from 2, 3 to n. Yeah, we call lambda 1 dominant eigenvalue, and the associate eigenvectors dominant eigenvectors. Okay. Yeah. Okay. Yeah. This is one more. Number 4. Yeah. A has n linearly. This is important. Independent eigenvectors. Yeah. Say psi 1. Yeah. Psi 1 associate with lambda 1. Psi 2 associate with lambda 2, and so on. Psi n. Yeah. So the basic power method has many assumptions. So yeah, you need to do research, how to remove these conditions, assumptions one by one, and make your power method still works. That is research we need to do, but there are many research in this area. But okay, I only present the most basic, so I made many assumptions. Okay, now power method. I want to this is what I want to find. Okay, yeah, I want to find this. Okay, and also I want to find this. Okay. How? How? Arbitrarily pick a vector. Yeah. Arbitrarily pick. Okay. Take a vector V. Okay. Now power. Okay. Power. Set V0 to V. Then compute what? V1 is A times V0. Compute V2 A times V1. And so on. In general, VK is A times VK minus 1. It turns out that VK, if K is large enough, VK is very close to psi 1. How to see that? Okay, yeah. By assumption, these eigenvectors linearly independent. So these eigenvectors form a basis for Rn. What it means? Any vector can be written as a linear combination of these vectors. Okay. Right. V as a linear combination of the vectors. Yeah, linear combination. That means that lambda times psi 1 vector, lambda times psi 2 vector, and so on. Cn, right? Hey, now a claim, okay? A claim, okay? What a claim, okay? As K large enough is very close to, yeah, this is what I claim. I want to show you, okay? Yeah. Right. Now, okay. What is VK? Actually, VK is equal to A to K times V0, right? Okay. Okay. What is it? VK. VK actually A power K times V0. Can you see that? Okay. Now apply A power K to the both sides. Then again, here implies that AK V is C1 AK psi 1 plus C2 AK psi 2 plus Cn AK psi n. Okay. By assumption, sign these vectors eigenvectors. That means that A times psi 1 is lambda 1 psi 1. Okay. Apply A to the equation K times. So again, this is a C1 lambda 1 to K power times psi 1. Here is a C2 lambda 2 K psi 2 and so on. Cn lambda n K psi n, right? Okay. Okay, then I take lambda 1 K out. Okay, then lambda 1 K C1 psi 1. Now second term. C2 take lambda 1 out. Lambda 1 to K times psi, yeah, and so on, yeah, plus Cn, okay, here, lambda n, lambda 1 to K psi n. By assumption, lambda 1 dominant eigenvalue. So this number less than 1 in absolute value. Yeah. And this less than 1 in absolute value. How about this? Constant, okay? doesn't depend on K. So when K very, very large, compare when K is large, right? Second term is small. Do you agree? All the other terms small. Okay. Yeah. So this term dominant. Okay. So this is a what? Roughly is lambda K, lambda 1K times C1 psi 1. When K very large. Yeah. This symbol K much larger than 0, very large. So when K is large, VK roughly is some number times psi 1. Eigenvector. Some number times an eigenvector, still an eigenvector. You agree? How to see that? Okay, yeah. Maybe, yeah. V is an eigenvector. Okay. Yeah. Any number times V still eigenvector. How? Multiply arbitrary number. Okay. Multiply C. Yeah. So I move C. Yeah. Lambda C. So if V is an eigenvector, then any number times V eigenvector. Say okay, here C1. We don't know C1, but C1 exists. Okay. C1 scalar, lambda 1 scalar. Scalar times eigenvector. So still eigenvector. All right, yeah. So I have solved the problem about how to find the dominant eigenvector. Yeah. This vector, dominant eigenvector. Now, how to find the dominant eigenvalue? How to find lambda 1? How to find lambda 1? Yeah. Lambda 1. We have VK roughly is lambda 1 K times C1 times what? Eigen. Yeah, C1. Yeah. We have roughly have this equation when K is very large. Now, how to find out lambda 1? How to find lambda 1? Take one entry from the vector on the left side and the vector on the right side. Say, take the I entries on both sides. Okay. How about the I entry? How about let me use this notation? Yeah. By this notation, I mean the I entry of a vector. Okay, so this is a roughly is equal to K times C1 times I entry. Yeah, scalar number times a vector. The I entry. So this is a lambda 1 K C1. We don't know C1. We don't know lambda 1. This is a sine 1 I, right? Okay. I entry. Hey, now how to get lambda 1. Take a ratio. Okay, so here V K I. Okay, VK is available because we just multiply A to vector V. So VK available. Okay, so this is available. Then over V K minus 1. This vector, the I component, I entry. So see what is that? Okay, roughly is here lambda 1 K times C1 times psi 1 I entry. Then over lambda 1 K minus 1 times C1 times psi 1 I entry. Do you agree? Alright, now I can see that I can cancel C1. I don't know C1 actually. I can cancel psi 1, the vector, eigenvector, the I entry. I don't know actually. So cancel. How about lambda K minus 1? Cancel. So this is lambda 1. So it turns out that VK is vector computable. I can get this vector. Then pick one entry, say the I entry, say the first entry, say pick the first entry. First entry over the V in the previous step, the first entry, take a ratio, okay? Then that ratio will approach lambda 1. Let me show you one example. Hey, here, take a look at this example. I need this formula. Here, I need this. I need this. And also, what I need is here. I need this. Okay. Here, this is a V K. Okay, roughly. Roughly. When K is very large. Okay, I need this, and also this. Okay. Okay. Now let me erase the other part. Hey, take a look at this example. A toy problem, of course. Okay. Consider this matrix. Size is very small, 3 by 3. Okay. 3 by 3. Actually, you can know by hand to find eigenvalues. You don't need computer. 2, -4, 9, 2, -2, 7. Okay. Easy to get eigenvalues by hand. Okay. Its eigenvalues and eigenvectors. Okay. Easy to get. Okay, except eigenvalues and eigenvectors. The dominant eigenvalue is 3. Corresponding eigenvector is 1, -1, 3. The other two eigenvalues, lambda 2, negative 2, eigenvector is 0, 1, negative 1. Now, the third eigenvalue, lambda 3, is 1. So, psi 3 is negative 1, 1, negative 2. Power method. Find this, okay? Find this guy, okay? And also find some scalar times this guy, okay? Some scalar times this. Yeah, here, some scalar, yeah. Actually, we don't know C1, but we know, some scalar times psi 1. This is a power method. Okay, now, now I need to, initially, I need to pick a vector. Okay, now solution. I pick a vector. This vector can be arbitrary chosen. Okay, yeah, pick a vector. Say, pick vector is 1, 0, 0. Yeah, transpose. Yeah, column vector. Transpose. Okay, now run power method. Now compare. VK. What is VK? Is A times VK minus 1. Actually, this is VK, AK times V. Times V. V0. V0 is equal to V. Now, let me make a table. Okay, table. Yeah. Table. Right here. First column is K. Second column is vector VK. The last column is this ratio. Okay, it is VK. This vector. Okay, first in this example I pick the first entry. Okay, I is 1. Then over V K minus 1. Yeah, first entry. Yeah. Suppose this number as K approaches infinity will approach dominant eigenvalue. Yeah, number 3. Okay. Yeah. Let's see. Okay. Right. Now I don't need this approximation. Okay. Yeah. This approximation. Yeah, will approach dominant eigenvalue. Okay. Eigenvalue. Yeah. When K is 0. When K is 0. Yeah. Here. V0 is equal to V. So the entry is 1, 0, 0. Yeah. Okay. K is 0. This ratio not commutable. Okay. Low this ratio because K is 0. V negative 1. What is V negative 1? Now K is 1. K is 1. K is 1. So A times V0. The vector is here. Okay, this ratio negative 1. Okay. When K is 2, negative 7, 11, 27, then 7. Right, yeah. When A is small, okay, now K is 3. Negative 25, 17, 69. Okay, now 3.5714. Oh, K is 3. Now this ratio, it is approaching the number 3, dominant, approaching the number 3. Right? K is 4. Okay. 79, 95, 455. Right? Can you see? Sk is increasing, Vk, the size, the magnitudes of the entries are increasing. Why? Because lambda 1 in this example is number 3. So when k is large, 3 to k, this number large times a vector. So actually, Vk actually is increasing in size, in magnitude. Okay, the magnitude is increasing. Increasing because 3 to k times C1. C1, we don't know C1, but it is a fixed number. Psi1 also fixed. Psi1 here also fixed. Yeah, lambda 1k go to infinity actually. So as a result, the magnitude of the vector is increasing. But this the ratio 1,6, 3.16. Continue. When k is 11, then wow, very large. Very large. This is a 5. Wow, large. Yeah. The entries of Vk large. But eigenvalue is very close to number 3. Computationally, this is a problem. Okay. A Vk magnitude increase to infinity. In some cases, the magnitude is super large, and your computer cannot hold those numbers in the case. The algorithm break down. Okay, stop. Okay, stop. It is possible even when the algorithm stop, this ratio still not converge to the dominant eigenvalues. Possible. This case, we say overflow. Yeah. Overflow. Stop. Hey. This example, lambda 1 greater than 1, number 3 greater than 1. So lambda 1 to k go to infinity. In some other examples, maybe dominant eigenvalue is less than 1, say 0.1. In the case, 0.1 to k go down to 0 very fast. Very fast. In the case, the magnitude of V quickly go down to 0. Then we call the situation underflow. Yeah, underflow. Underflow, overflow problems, okay, in computation. Yeah. If the magnitude too small and this converge very slow, so we cannot get the dominant eigenvalue. Yeah. This is how to overcome this difficulty. This difficulty. Yeah, we need to make improvement. Okay. So this is Friday. Okay. Today Wednesday, right? Friday. Yeah. I will present improved version of our method. Okay. Now in the version we try to avoid overflow, avoid underflow. Okay. Today is Let me stop 10 minutes earlier. Okay. So, yeah. Do you have questions? Say, Michael. So, what you are thinking? Yeah.
I was thinking, where did the lambda 2 psi 2, lambda 3 psi 3, where did those come in? Like, where did those get used?
Where? What do you mean? Psi, you mean this vector?
Yeah, just for 2 and 3.
2 and 3. A 3 by 3 matrix has 3 eigenvalues. It must have 3 eigenvalues. Associate with 1 eigenvalue, there is an eigenvector. This is an eigenvector associated with this. How? How to get psi 1? Yeah, here. How to get psi 1? Yeah. So, this equation. Say number 3. Solve this. Yeah. This is an eigenvalue, eigenvector equation. Solve this for x. How? Move right side to left side. And then write number 3 as 3 times identity matrix. Yeah, it's 0. Then a minus 3i vector r x. Yeah. Solve this linear system to get psi 1. Yeah, you can leave. Yeah, I can talk to Michael. Yeah, only. Yeah. Okay, let me stop.